So it says find the following. If no value exists, we can put dne. So we're going to look, okay, so this is all happening as we approach x is equal to 0. So we're going to take a look at the limit as we get close to 0 from the left side. So that's what this means. So we're going to be kind of approaching along the left side. It looks like our y value is tending towards -3 by the look of it. And then we want to take a look at what's happening as we approach 0 from the right side. Looks like we're also tending towards a y value of -3. So we could now take a look at our overall limit. It looks like overall, since the limit from the left and right hand side look the same, so we can probably say that this overall limit as we approach 0 is -3. However, our function's not defined, or it's defined at 0, but the output does not give -3. This is what the output is right here, this solid black dot. So it turns out that if we try to evaluate the function at 0, we should get -1. So kind of an interesting question. It means that the limit can exist, but the function doesn't have to be defined there, or it could be defined somewhere else. All right, looks like we're just looking at the limit as we approach -2 from the right. So -2 from the right is going to be like this way. So we're going to be coming along and looking at what happens as we get closer to an x value of -2 from the right, and it looks like we're tending upwards forever and ever. It looks like we're actually tending towards positive infinity here. So I think I'm okay with that. If we needed -2 from the left, we would get negative infinity. And of course, that would mean that our overall limit does not exist. It's a bad kind of discontinuity there. So if you haven't had a chance to look at some of the techniques that we can use to work with limits, like factoring or rationalization or things like that, what we could do is we could set up an expression inside the calculator. And we can kind of take a look at what's happening as x values get closer and closer to 7. So I could choose some x values. I could take a look at what x cubed minus 3x squared minus 29x plus 7 gives me. Or a whole bunch of different values of x. So it's a little tedious to do on the calculator, but I'm just going to go through, and wherever I see x, I'm going to put a set of brackets. So up here we'll get x cubed. I'll have a minus 3x squared minus 29x plus 7. And then we can cycle back through and just start picking some values that get closer and closer to 7. Specifically, we might want to take a look at a couple numbers like, I don't know, 6.9, 6.99, etc. And then maybe 7.1 and 7.01. So we could just try a couple from either side of 7, see if we end up getting the same reasonable decimal approximation, and kind of use that for our answer here. Yeah, exactly. If the answer is going to be in Z, that's a big hint. That usually means you can factor this thing. I agree. But do we really want to factor a cubic? We probably could, actually. It shouldn't be that hard. Maybe it's worthwhile to do that after. So let's try 6.9. The decimal output is going to be 74.21. And then I can cycle back through my calculators, add some 9s in. It's going to be click SMR here for a second. And I can do this for 6.999, etc., etc. I'm just trying to get a rough and reasonable. Maybe I actually will need to do maybe another one. 8201. So yeah, it's not super obvious. Maybe it's going to 76, but it's not really obvious after just 2 iterations. Maybe I'll do one more just to kind of see if my intuition is right. But yeah, if it's going to tend towards an integer number, it's probably going to get closer to 76. Yeah, there it is. So after the third iteration, I can be pretty comfortable we're probably tending towards 76 with the given hint. And then we can go back and kind of do the same thing for values that are slightly bigger than 7, so maybe 7.1. And it's a bit of a tedious process here. And I usually tell my students that this is kind of like the backup. Like if everything fails and you're not really sure what to do or things look really complicated, table of values is kind of your backup to kind of make an educated guess on what you think that limit's going to look like. So let's see, 7.1 gets us 77.81. We'll go back through and add that extra 0 in. And then maybe we'll take a look at how to factor this. In case you're curious about why this answer is going to be 76. So there it is, 76.18. And if we did one more step, we'd probably get even closer. So I'm going to guess that the following limit is 76. And let's take a hint. Yeah, exactly. So x minus 7, if this has a limit, x minus 7 has to be a factor of the numerator. So we can basically take x cubed minus 3x squared minus 29x plus 7. And then we can just do a long division procedure to try to get a quadratic out. Once we cancel out the x minus 7 factor, then we can just plug 7 into that quadratic, and whatever we get there should be the limit that we're looking for. So in our case, we're going to need an x squared. That's going to get us to x cubed minus 7x squared. Let's do a subtraction, and that'll give us negative 3 plus 7. Negative 3 plus 7, so that's 4. Next step is to compare the 4x squared and the x. So I'm going to need, 4x? And then multiplying those out, we get 4x squared minus 28x. Do a little subtracty, and we should get negative x plus 7 as our last bit. So that's going to be a minus 1. That's going to give us our 0 remainder that we're looking for. So we can basically rewrite this limit as an x minus 7. So that's that factor that we thought divided evenly into the x cubed term, or the x cubed polynomial. That's going to return back to us this x squared plus 4x minus 1 polynomial. These x minus 7s end up canceling out because the limit's not really concerned about what happens directly at 7, so we can get rid of those very small decimal numbers that we're going to get as we get close to 7, and then we're going to be left over with x squared plus 4x minus 1. So we can now substitute 7 in. So we should be able to get like 7 squared plus 4 times 7 minus 1, and that's 49 and 28 minus 1. Is that 76? I hope it's 76. So 48 and 28 is 76, I think, right? 76. So there we go. So there's kind of our more algebraic proof that should be the case, but it does involve a little bit of legwork here to kind of figure out what that quadratic factor is for the x cubed bit. Let's take a look at how to do this on Desmos. So for my students, Desmos will give you a little bit of a faster edge than using your calculator, although your calculator should work as well. But the nice thing about Desmos is you can come in here and you can define a function. And what we're going to do specifically is we're actually going to define this particular function that's given to us. So I need brackets, divided by, and brackets, just to kind of get everything set up. And then sqrt will give us the square root function. So we can go square root x minus 11, and then x minus 121. So here's our function. And now I can start evaluating this at whatever number I want. And specifically, we're going to be interested in what's happening close to 121. So maybe let's do 121.1, let's say, right? And we'll do f at 121.01. And we'll do f at 121.001. Right, so we can kind of see that after a couple iterations, we're going to get 0.045 in each case, 0.045. So that's for values slightly larger than 121, And then we'll just want to circle back and do values that are slightly smaller than 121. So maybe things like 120.99. We'll do f at 120.999. So just a couple iterations here for values slightly smaller than 121, but I can see that I get that 0.045 back again. So I think my answer here is 0.045. And what we can do actually is maybe we can use Serino's idea. So Fem has given us a closed form of 1 over 22. And let's take a look at Serino's idea here. Serino says, why don't we think about maybe the denominator as a difference of squares? So we're going to look at x take 121. And I recognize this as 11 squared. Now this one's a little bit trickier to recognize, but this one is root x squared. So using our difference of squares formula, it's going to be root x plus 11 and root x take away 11 in the denominator. That's going to allow us to cancel off that particular factor that's causing this singularity. And then we're going to be able to go ahead and sub in 121. So we're going to get the square root of 121 plus 11. And I think that's where we get our 1 over 22. Nice. What is our function? Our function is, oh, this is weird, the absolute value over x minus 4. So 5x minus 20. Ooh, and that looks very odd. So my guess is as we're approaching 4 from the right, so that's the dot that I have floating around right now. As we approach 4 from the right, we're going to get positive 5 by the looks of it. I'm kind of ignoring these like little nubs pointing downwards. I think that's just a graphical error from Desmos. So I can see that as I approach 4 from values a little bit bigger than 4, my y value is tending towards 5. And if I approach values of 4 a little bit smaller than 4, I'm going to get negative 5. Right, so there's 3.99, negative 5. So for this first one, it looks like we're getting negative 5. For the second one, we're going to get positive 5. So obviously this overall limit does not exist because these two one-sided limits would be different. Yeah, and a lot of the way that we think about working with these absolute values is we might say, okay, for values, so like let's say x was bigger than 4. Then what can you tell me about 5x minus 20? Well, if x was bigger than 4, this number would be slightly bigger than 20, wouldn't it? So this number must also be bigger than, this must be bigger than 0. Or you can argue maybe like this. We can maybe multiply both sides by 5. And so we know 5x take 20 must be bigger than 0. However, if x was less than 4, then 5x would be less than 20. And now 5x take away 20 would be less than 0. So that gives me information about how I can take this 5x minus 20 and reduce it to something else. So this 5x minus 20 over x minus 4, we can really rewrite this as, in the first case, as 5x take 20 over x take 4. So that's this first case. Sorry, that's this case here. And then this is going to simplify to 5 when we factor and cancel. Now in the second case, maybe I'll just draw the path in red. So for the second case, this is our second case. And then when we go to take a look at the absolute value of 5x take 20, now that absolute value is actually smaller than 0, right? So this value is smaller than 0. So to make an adjustment, we're just going to add this negative sign out front, right? So now that makes sure that this 5x take 20 is going to be a positive number. And then I can go through the same procedure of factoring and canceling, and we should end up with negative 5. So that's typically kind of approach that I might show my students when working with absolute values.